Hi everyone, and welcome back to my channel. If you haven't subscribed, do well to click the subscribe button. It's totally free. Okay, before we move on with MSTs, I thought we should grab a very quick example on any of the scheduling algorithms. So on this example, we are going to be minimizing the weighted sum of completion time. This is a sort of refined version of minimizing wait times. You should, pause the video, read the question, and let's look at the solution. So for this problem, first off, the completion time for each job. Supposing the first job is job J, the completion time for job J is, let's call it CJ. But if job J is the second job, that means maybe it has job I before job J, then the completion time for job J becomes TI plus TJ, right? So we can say that the completion time, let's call the completion time of job J, completion time of job J would be the sum of the sum from I equals 1 to J of TI. So the sum of all jobs including J, the sum of the time of all jobs before J including the time for J, that's the completion time for job J. And the total completion time of all jobs, total completion time would be this. CI, where CI, let's call the completion time of job J, let's call it CJ, right? So the total completion time of all jobs will be the summation of from I equals 1 to N of CI, and the total weighted completion time of job would be, this would be the total weighted completion time and our goal is to minimize the weighted sum of completion time. And we are going to solve this question making some assumptions. The first assumption is that the time required for each of these jobs are not equal. The second assumption we are going to make is that the weights are also different. So according to the question, each customer has a given weight, and this weight represents his or her importance to the business. So we want to solve this problem in such a way that the customer that is of most importance to this company is the happiest, right? So having this in mind, we want to create a second variable. Let's call it the priority, right? The priority of each customer. So let's say, because we want to schedule in decreasing order of weights, right? We want to attend to customers with the highest weight first, like that. We want to solve this problem in decreasing order of weights. That is, we want to solve it this way. And we also want to solve in increasing order of time. That means the one with the least time comes first. These are two different variables. So we would find a way to combine these two variables. Let's call some combination of these two variables a priority, and we'd get the priority by, let's say, we could say weighted time, weight over time, right? And since weight is being since we are solving by decreasing order of weight and by increasing the order of time, this would mean that the ratio weight over time, let's call this WI over TI, right? So if we use this ratio, let's call this ratio the priority. So with this formula for priority, it means now we are going to be solving W1 over T2 greater than, in this order, W2 over T2, and going forward. And if you look at this, it makes sense. Supposing, let's visualize this with numbers. Supposing these weights go from, let's say, 20, 15, 10, that way, and the time goes from let's say 5, then 10, then 15. We see that for WITI, 20 divided by 5 will be 4. WTT2, 15 divided by 10, that will be 1.5. You see that with this ratio for priority, the first is greater than the second is greater than the third, and that way until the end. But if we decide to use the converse ratio for priority, that is time divided by weight, we would see that instead of this decreasing order, it will become an increasing order. That is Ti over Wi less than Tj over Wj less than, that way. Let's say T1 over W1 less than T2 over W2 less than T3 over W3. So the converse, if we use the converse ratio, that's time over weight for priority, instead of this, we would have increasing order of T over W's for each of the customers. That's just what we're saying. Okay, let's move on. So this priority is going to ensure that the summed weight of completion time is minimum. Let's look at an algorithm for solving this. Okay, so for each job, we are going to divide its weight by its processing time and call this the priority. So the algorithm, number one, calculates or find priority for each job. Then we are going to sort all priorities in decreasing orders. Sort priorities in decreasing order. Then we are going to schedule jobs using this sorted list. So to prove this, we would use, so far I hope that everything is super clear. Let me reiterate everything I've said so far. We want to schedule these jobs based on two variables: the weight, which signifies the importance of each customer to the company, and the time of the jobs. Now, if you look at the example that has been given in this question, we see that scheduling only by the weight would not optimize, would not give us the optimization we want. And scheduling only based on the time of each job will not make the most important customer happy, or happiest. So we would find a way to combine these two variables to achieve our goal. And combining these two variables, we decided to use weight over time. The ratio weight over time is what we call the priority. Now, I said that if we use the weight over time, we are going to be scheduling these jobs and decreasing order of weight over time for each customer. But supposing we use a converse ratio, that's time over weight, which you will also call the priority, we'd notice that the scheduling of this job will no longer be in decreasing order, it will be in increasing order. And here's the algorithm for scheduling these jobs. Now we're going to go one step further by proving, by writing a proof for this problem. And we are going to be using the proof by exchange of property. So the greedy algorithm sorts the job in decreasing order of priority. This using this scheduling based on priority is greedy, and this greedy algorithm sorts the job in decreasing order of priority and schedules this job in this order. So we want to consider any other optimal solution where the jobs are not sorted in decreasing order of priority. So this is a proof by exchange of property. So let's consider an optimal algorithm. Let's call it OPT. So let's say that for our OPT we have jobs scheduled in this manner. We have all jobs from the beginning to this point. Let's call it T prime. Then we have job I, job J, and the rest of the jobs. And job I will take TI time, job J will take TJ time, and the weighted sum of all jobs would be WI CI plus WJ CJ. Let's take that down. The weighted time of all jobs from T prime to I would be, the weighted sum of all jobs would be WI CI plus WJ CJ, which would be WI CI would be T prime plus CI, and WJCJ would be WJCJ, that would be plus WJ T prime plus TI plus CJ. In writing this, is going to be written as T prime. We have our T prime and WI plus WJ plus WI plus WITI. We have T prime. We have WI multiplying everything here plus WJ multiplying everything here, and when we refactor, we're gonna have T prime WI plus WJ plus WITI plus WJTJ plus WJTI. I hope that is clear. So this is what we have from the optimum. Now let's consider another algorithm. Let's wipe the first part. Let's consider another algorithm. a new algorithm. Let's call it a new algorithm. Let's consider a new algorithm where J and I are switched. So this is a new algorithm. We have the scheduling. We have T prime, then we have J, we have I, and the rest. So if we switch this, the weighted sum of all jobs would be from all jobs from the beginning up till J would be WJCJ plus WICI, which would give us WJ. Remember the formula for CJ? We talked about this at the beginning of the video. CJ, that will be the completion time for J. That will be T prime plus TJ. Then we have WI, completion time for I, that will be T prime plus TJ plus TI. And when we refactor, when we open our brackets and refactor, we would have T prime WI plus WJ plus WITI plus WJTJ plus WITJ. How are these two really different? So we find that the difference is in the last factor. We have WITJ and WJTI. So everything, the first term is same, second term is same, third term is same. So we see that WJTI is not equal to WITJ. So our conclusion now is that if WJ, this is our conclusion, if WJ over TJ, that's the priority for J, right? If the priority for J is less than the priority for I, that's WITI, we switch positions of jobs J and I. We switch positions of jobs J and I. I hope we're going to stop here, and that's that's the solution for this problem. I hope you enjoyed this video. If you did, remember to subscribe. It's totally free, and comment, like, and I'll see you on the next one where we'll be continuing with MSTs. Thank you.